Greetings, Gen Chem students. This is a little session, a Zoom session designed to help you prepare for the Line Spectra lab report. So you'll prepare the best, most complete lab report for this exercise so you can show that you've learned the material and get as high as grade as possible. So there are 4 parts to this Line Spectra lab, part A, B, C, and D, as described in your lab protocol. And we're going to look what the requirements are for each of those 4 sections with respect to your responsibilities and what needs to go in the lab report for those 4 sections. So let's look at the sections. We'll start with part A. Part A, you look at the YouTube videos. Watch the YouTube videos that are linked in your lab report. Not your lab report, in your lab protocol. The links are given to take you right there to the YouTube videos. There are 4 of them. Watch them. Okay. Then that's what you need to do for part A. Then part B. This is where has to do with the videos from part A that deal with line and continuous spectra. And what you should do for your lab report in this section is to describe in your own words and discuss in your own words the demonstrations and explanations of line spectra and continuous spectra that you saw in the YouTube videos from part A. So you watch those videos in part A, and then in part B, you're going to give your own description and discussion of the demonstrations that you saw in those videos of continuous and line spectra. Show me that you understand what they are, where they come from, how they differ, and why it matters. That's part B. That's pretty simple and straightforward. Now, going on to part C. Okay, so we're on to part C of the Line Spectra lab report and what you need to do for your lab report for that lab exercise. And part C is testing the Bohr model, the Bohr theory for the structure of the hydrogen atom. And this is a diagram. I'm having trouble, by the way, with the lighting and with the angle of my camera. And you can see they're kind of blurred out here by the lights. I can't seem to get that to go away. So I'm going to do the same lecture that we're doing here on Zoom. I'm going to do it on Show Me, and I'm going to post that along with this Zoom video under the online lab protocols with the lab protocol for the Line Spectra lab. So you can look at that if this isn't looking good on your computer or when you're pulling it up and watching it. On Show Me, you won't be able to see me, which would probably be a good thing, but I think you'd have a more clear description or visualization of what's being done on the board. But let's go ahead and finish this. So part C, we're testing the veracity, the ability of the Bohr model of the hydrogen atom to predict and explain what nature does, what the hydrogen atom does. More specifically, the model supposedly proposes to explain and predict the line spectrum of hydrogen. And that is, it proposes a physical mechanism by which the discrete lines that show up in the hydrogen line spectrum it provides a physical mechanism by which these discrete lines, these discrete wavelengths, these discrete colors of light are emitted or created by the hydrogen atom. And recall that the old physics, before quantum mechanics came on the scene in the early part of the 20th century, the old physics could not explain this line spectrum at all. It didn't fit. It didn't fit with the old physics. It would be like trying to squeeze a round peg into a square peg into a round hole. It just didn't work. So Niels Bohr, that Danish physicist, created a whole new physics, a new model that he claimed could not only predict the colors and the energies of these lights emitted by excited hydrogen atoms, but he said could also explain them, how they were created, because his model provided a mechanism. And you know what that mechanism is. You should know from reading chapter 6 in your textbook and also from watching the quantum Show Me videos that I posted in weeks 3, 4, and 5. And actually Show Me videos 5, 6, and 7 and week 4 materials talk specifically about the Bohr model and the mechanism by which it produces these lines, these colors, these energies of light. So here's the Bohr model. The nucleus of the hydrogen atom sits in the center. And remember that Bohr assumed that the electron could not exist just anywhere within the hydrogen atom, but could only exist in orbits certain distances, very specific distances away from the nucleus. And he gave them numbers, like n equals 1 was the orbit that was closest to the nucleus, then n equal 2, 3, 4, 5, 6, 7, 8, 9, just goes on and on. Now, when the hydrogen atom is in its ground state, its lowest energy state, we call that the ground state. It's where it's happiest, its lowest energy state. Its electron is in the n equal 1 orbit, the one that's closest to the nucleus. And that makes sense because the nucleus is positively charged, the electron is negatively charged, and negative charges love positive charges. So by getting as close to that positively charged nucleus as possible, it lowers the energy of the atom as much as possible. So this is where you find the electron under normal conditions, ground state conditions. However, if you hit it with electricity, if you heat it really hot, if you energize the atom in some way, you can kick that electron up to a higher state. Let's say that the n equal 5 state, that orbit. Now it's further away from the nucleus, and by being further away from the nucleus, it's in a higher energy state. And now it's not going to like being there, and given the opportunity, or as soon as it can, it's going to drop back down to that low energy state. And as it does, it's going to release, or it's going to shake off, shed that excess energy in the form of light, a photon of light. And so we get this photon of light zooming out of the atom. And that photon of light has a very specific energy. The energy of that photon that's being emitted is exactly the same as the energy difference between the electron in this orbital number 5 and the energy of the electron when it's in orbital number 1, in this example case where the electron is going from n equal 5 to n equal 1. So we have a very specific energy of light, therefore we have a very specific color of light and a very specific wavelength of light. And that describes the line spectra. Okay. So we're going to test this. And the first thing you want to do is look at the table 1 in your lab protocol, and it looks something like this. And you're going to fill in this table. Now, these last 2 columns, you're going to fill in by doing calculations using the Bohr model's equations. And you're going to fill in the energy of the electron undergoing, or the hydrogen atom undergoing these transitions. And you're going to fill in the wavelength of the emitted photons as the electron undergoes these transitions within the hydrogen atom. Now these are going to be the first 2 columns after the transition column. These are the experimentally observed color of light emitted and wavelength of light emitted. And we'll talk about those in a moment. So here are the 3 transitions that we give you in the problem and part C, testing the Bohr model. We have the electron going from n equal 5 to n equal 2. Notice we have n subscript I, that means the initial orbit, going to nf, subscript f, for n final. So going from state 5 to state 2. Another one that I gave you, a different transition, 4 to 2, and another was 3 to 2. And as I said before, we're going to use the Bohr model to calculate the energy and wavelengths for these transitions. And we're going to fill them in. You will fill them in and put this in your lab report, this table. So let's go ahead and do that. Let's demonstrate how you'll do that. And again, if you look at, I believe it's show me video 5 or 6 that goes through these very steps that we're going to do now. So what we want to do right now is, let's start with the first one here. We'll do one example, the transition of a hydrogen atom undergoing an energy transition from the n equal 5 state to the n equal 2 state. right? So that would be like we did here, but the electron would be going from n equal 5 to just n equal 2. And we want to know what is the energy of that photon that's released and what is the wavelength of that photon that's released. And we're going to use the equations that come out of Bohr's theory, the Bohr model. Remember, Niels Bohr was the Danish physicist who came up with this model to explain the line spectra of hydrogen, the internal structure of the hydrogen atom. And so these are the equations we're going to use. So first we're going to plug into, we're going to find the energy change of the atom as the electron goes from Ni, initial state of n equal 5, to a final state of n equal 2. So we use that equation. So let's do it. So delta E is equal to E photon. Now what does that mean? Well, delta E is the energy change that occurs within the atom as the electron drops from 5, n equal 5 to state 5, from state 5 to state 2. And since the photon is what carries away all of that energy, the energy of the photon must be equal to the energy of the change, of the energy change that occurred within the atom. So the energy of the photon is going to be given by this equation, and R is equal to 2.18 times 10 to the negative 18 joules. That's given in your protocol. This is called the Riemann coefficient. And now what is our Ni? What's our initial state? Well, remember we're looking at the 5 to 2 transition. So Ni, we have 1 over Ni squared, so that would be 1 over 5 squared, because we're starting in the 5th orbital. Minus 1 over N final, where we end up. Well, where do we end up? We end up in the 2nd orbital, so 1 over 2 squared. Don't forget the square. So that's going to be equal to 2.18 times 10 to the negative 18 joules times 1 over 25 minus 1 over 4. And then you do this again, 2.18 times 10 to the negative 18 joules. And that is equal to negative 0.21. That is 1 over 25 minus 1 over 4 is equal to 0.21. And you multiply that through negative 0.21, multiply that through by the Rydberg constant, 2.18 times 10 to the negative 18, and we get 4.58 times 10 to the negative 19 joules. And that is the energy of the photon that would be emitted as an electron goes from the n equal 5 state down to the n equal 2 state. Goes from a high energy to a low energy. The atom gives up that excess energy as a photon, and that would be the energy of the photon according to Niels Bohr's model, his theory. So we can plug that in over here. What is the calculated energy of the from the Bohr model for the 5 to 2 transition? It is 4.58 times 10 to the negative 19 joules. There, so we've gotten the calculated energy using the Bohr model. Now we need the calculated wavelength. Well, that's given by this equation. Well, it can be calculated from that equation, because notice what we have here is hc, Planck's constant, times the speed of light divided by the wavelength is equal to energy of the photon. Right? This is equation 3, I think, in your protocol. What we want is the photon wavelength. That would be lambda. So we just rearrange this equation, and if we solve for lambda, we're going to have hc over the energy of the photon. Now we just plug and chug. What is h? H is Planck's constant. That's given in your protocol. That is 6.6 times 10 to the negative 34 joule seconds times the speed of light. That's what c is. And the speed of light is 3 times 10 to the 8th meters per second, again, given in your lab protocol. And now we just plug in the energy of the photon, which we know from the first step up here. And the energy of the photon is 4.58 times 10 to the negative 19 joules. Now notice we dropped a negative sign here when we did the energy of the photon. We did that on purpose. We're actually taking the absolute value. The energy change of the atom went down as the electron went from the n equal 5 high energy state to the n equal 2 low energy state. But all that energy was taken away by the photon. So the photon doesn't have a negative energy. Its energy is positive. It's carrying away all of that energy that was lost by the atom. So we just put plus there. We don't have the negative. Now you do your calculations, your plug and chug, and we get a wavelength of 4.3 times 10 to the negative 7 meters. There you go. That's the wavelength. But we're asked to give the wavelength in nanometers, right? So again, this is given in your handout. There are 10 to the 9th nanometers per every meter. So the meters will cancel, and we get 430 nanometers. Actually, you get 432 nanometers, I believe, yes. And that's what we put into, that's the wavelength of the emitted photon. So this photon has an energy of 4.58 times 10 to the negative 19 joules, and it has a wavelength of 432. Thus says the Bohr model for the hydrogen atom. So we're going to plug in 432 nanometers. Now, what do you do with this? Now you're going to fill in these other, you would do the same kind of calculation for the 4 to 2 transition and for the 3 to 2 transition. And so you get these last 2 columns filled in. And now you're going to look back over here and decide which of these transitions goes with which wavelength. So let's see. Now we can put in our, now we look at our experimental data. This is our observations. And where do you get your observations? You didn't really run the experiment, but we did the simulation of the experiment through those online videos, those YouTube videos. And you have this in your lab protocol that came from that simulation of that experiment. And here is the line spectrum of hydrogen. And you can see this, and there's our scale, our wavelength scale. Now, notice that the wavelength here, this blue line, has a wavelength of around 430 to 440, right? So, and what did we get in our Bohr calculation for the 5 to 2 transition? We got 432 nanometers. So this observed line color would match this blue line. So we'll say blue seems to match with what the Bohr model predicts. And what was the observed? Now this is the experimentally determined wavelength, not calculated using Bohr's model. And you write down, you find on this scale where it is. Now you can only record 2 sig figs, not 3. So this is going to be somewhere between 430 and 440. But we have a cheap $10 spectroscope that we were using to find the locations of these lines. So we can only get to a precision of 2 sig figs. So I'm going to write 430. And that last digit is uncertain. We don't know what it is. Okay. So now you'll do the same for the 4 to 2 transition. You'll calculate the energy using, doing just what we did here. But now for the second transition, in I is going to be 4, and in final will still be 2, just like it was here. But this was 5, n equal 5. We're going to put n equal 4. This will still be n equal 2. Square those numbers, do the calculations, and then calculate the associated wavelength. Then do it again for the 3 to 2 transition. And then plug in those numbers and determine which color of light goes to the 4 to 2 and 3 to 2. And notice that you can see the colors of, oops, do I have that upside down? I had it upside down, sorry. Did I have it upside down before? Probably. So your blue was 430 something, and you have a red around 600 something, and a kind of a greenish one between 450 and 500, these experimentally measured line positions. And you'll be able to determine which observed color, the red or the green, go here or there. And notice that you can then determine the wavelength of those, the experimentally determined wavelength, which goes in there. And based upon the results that you generate for this table, you're then going to make an evaluation of the ability of the Bohr model to predict what nature does. That's what good theories do. A good scientific theory allows us to predict and explain what nature does, what matter does. And if Bohr's model, the predictions from his equations, predict what we observe physically, experimentally, then we would say it's a good model. But his model wouldn't only predict. If it does predict correctly, then you say, yeah, it's a good model. But good models also explain why the lines are the mechanism for what's happening. And the Bohr model does provide that mechanism, right? Because it says, this is why it produces these specific colors of light, because of these specific orbital energies and these equations that go with it. So that's part C. And then there's part D. Okay, so now we're looking at part D. This is the last of the 4 parts for your Line Spectra lab. And remember, you want to put add something in your lab report for each of these 4 sections, A, B, C, and D. And so what are we doing with part D, and what are you going to put in your lab report? Well, part D has to do with determining the ionization energy of the hydrogen atom. And remember what ionization energy is. That's discussed quite well. I shouldn't say quite well, but it is discussed in the Show Me video that I just posted today under week 6 materials. But ionization energy of hydrogen would be taking your hydrogen atom with its single proton and its single electron and taking away that electron, such that we're left with a positively charged hydrogen atom because we plucked away its electron. The energy required to remove an electron from an atom is called its ionization energy. And every atom in the periodic table, all 93 or so, however many there are exactly, I don't remember, every atom has its own unique value for stealing its outer valence electron. And that's what we want to determine for hydrogen. What is the ionization energy, the energy required to remove an electron from an atom? And remember, electrons are in atoms because they're attracted to that positively charged nucleus. They like it there, they're attracted to that nucleus. So it's always going to take work. It's always going to take energy to pull an electron away from that atom whose proton the electron is being attracted and held by, being attracted to and held by. So in part D, what you're going to do, here's a diagram of the Bohr model of the atom. There's the nucleus, and here are the different allowed orbitals, n equal 1, n equal 2, n equal 3, and then we jump up to n equal 10, n equal 50, 1,000, 10,000. They just keep going on forever. Well, not forever, but for large numbers. And what you want to do in this lab is you're going to determine, this part of the lab, you're going to calculate using Bohr's model, the Bohr model equation. You're going to calculate the energy for an electron being pulled from the n equal 1 state, the ground state, the lowest energy state, up to n equal 2. So how much energy would it take to pull an electron from its lowest energy state out 1 step to the n equal 2 state? Remember that the electron is in its lowest energy, happiest state when it's in n equal 1. So it's going to take energy to pull it away a bit. How much? Well, you use this equation. This is the Bohr model equation. We want the energy as the electron is pulled from n equal 1 to n equal 2 state. That's going to be equal to delta E of the atom, the change in the energy of the atom, which is equal to the Rydberg constant, that R constant, whose value is 2.18 times 10 to the negative 18 joules, times 1 over the initial state orbital squared minus 1 over the final state orbital squared. And that's all you do. So you do 2.18 times 10 to the negative 19 joules. And if you do that calculation, you're going to get 1.6 times 10 to the negative 18 joules. Okay? So that's how much energy is going to be required to do this. Take the electron right there where it's happiest and then pull it out to there. Now you're going to do the same calculation again, but now you're going to see how much it takes to go from n equal 1 to n equal 3. And you're going to do the same kind of calculation, but now n1 will still be the first state, n equal 1 state, and now the n final will be n equal 3. And you'll get a higher energy because you're having to pull it further away from the nucleus where it wants to be. It's going to take more energy. And then you keep doing that. You go up to, you do it from 1 to 2, 1 to 3, 1 to 4, 1 to 5. So 1 to 5 would be equal to the energy for that transition, pulling an electron from the n equal 1 state to n equal 5. It's going to be equal to the Rydberg constant, 2.18 times 10 to the negative 19 joules, 1 over the initial state squared, that's 1, minus the final state. Well, we're looking at this one now, going all the way out to n equal 5. Right? And so you'd plug in 5 squared and do the calculation, and you'd find that the energy is 2.0 times 10 to the negative 18 joules. Now notice it's larger, right? It takes more energy because you're pulling it further away. And let's say we do it for the energy for pulling an electron from n equal 1 to n equal 10. So you do the same calculation again, and you see 2.18 times 10 to the negative 18 joules. That's the Rydberg constant times 1 over the initial state of the electron. That's in the n equal 1 state squared minus, now we're looking at this one, going from n equal 1 all the way out to n equal 10. So 1 over 10 squared. And when you do that, you get 2.16 times 10 to the negative 18 joules. And notice that it's larger yet. It's taking more energy each time you pull the electron further away from the nucleus, which makes physical sense because the electron is attracted to, held by that, by the attractive force of the positively charged nucleus. And you'll continue to do that as explained in your lab protocol all the way out to n final of 10,000. Now you don't do one step all the way out to 10,000. You can see in your lab protocol the steps that are required, but you need to provide those energies for those transitions that part D requires you to do. 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 10, 1 to 25, I think, 1 to 50, 1 to 100, 1 to 1,000, 1 to 2,000, something like that. Do all those energies. And what you're going to see, if you were to plot the energy required to pull the electron out as with respect to the final end state, quantum, final orbital state in F, you'd see that the energy does this. It's increasing, right, as you take it further and further from the nucleus. But then it starts to level off. And at some point, it becomes completely level, flat. We got the light shining right on that. That's too bad. And the ionization energy is going to be where this hits what's called an asymptotic limit. At some point, no matter how far you pull the electron away, the energy required to pull it another step doesn't go any higher. At some point, you've pulled the electron so far away from the nucleus that it no longer sees or feels the attraction to that nucleus. And therefore, it's not going to take any more energy to remove it any further away, because that's the only thing that's requiring energy to pull the electron out is its attraction for the nucleus. Once you get far enough away from the nucleus, then it no longer feels that nuclear attraction and it takes no more energy. And you'll see that these energies that you're calculating level off to some specific value. It's not that value, it's going to be a little higher than that. But that would be the ionization energy. So where this graph levels off, that energy right there is the ionization energy for the hydrogen atom. And what you're asked to do in the report is to report the ionization energy. Oh, this would be the ionization energy per atom. When you find it using that kind of graphical relationship, doing what we're doing here. But we want, and your report asks for the ionization energy of hydrogen per mole. So you'll have the ionization number, whatever that is, 2.18 times 10 to the negative 18 joules per atom. You need to convert that to a mole per mole basis. And so you just multiply through by, there is 6.02 times 10 to the 23rd atoms per mole. Right? And atoms cancel, and now you'll end up with the ionization energy per mole. And that's what you record in your lab report. And now find out, look on the web, what the ionization energy, the experimentally determined ionization energy for hydrogen is, and compare that to the ionization energy that the Bohr model, this is using the Bohr model, this theory, to calculate or predict the ionization energy for a hydrogen. So look at your value, the molar ionization energy for hydrogen, look up online and find out what it is, the experimental value, and then calculate the relative percent error of Bohr's model to the known experimentally determined value. I think you'll be impressed, should be anyway. And write about this, discuss it in your lab report. So we've got a lot of problem with the lights here and the angle of my camera. I'm not sure what's going on. But as I said, I'm going to do the same kind of calculation or these same steps. I'll go through them in a show me video, and I'll post that on D2L in the same place where the show me video is posted with the Line Spectra lab protocol in that area where it says online lab protocols. So if you have any questions, if this doesn't make sense, if you need help, send me an email, call me. Happy to get calls. And we can set something up or do it. And I hope to have a Zoom online video meeting on Wednesday, but if I still have Wednesday evening at 7 o'clock, but hopefully I can work out my camera issues here, but we'll see. All right, that's the story. Stay healthy. God bless.